All right, so I'm going to give you the general procedure for solving an ordinary differential equation using Laplace transforms. So normally we would go from the t domain or time domain to the Laplace domain. That's what it means, solving an ordinary differential equation using Laplace transforms. We're going to go from the t time domain or time domain, t domain. So we have, I would say, time domain. To the t domain or Laplace domain. So t domain to s domain or Laplace domain. So referred to as s domain. Right, so the ordinary differential equations will be obtained from the process modeling principles. You obtain them. Remember, the objectives of linearization was that you should be able to identify whether a given differential equation is nonlinear or linear. So once you're able to identify whether it is linear or nonlinear, then you can proceed depending on what you have at hand. If the ordinary differential equation that you have is linear, then you can go straight away and take the Laplace transform of the ordinary differential equation. However, if the differential equation that you have is non-linear, your task will be to linearize the nonlinear differential equation before you could take Laplace transform, because Laplace transform can only be taken for linearized or linear differential equation. That's very important to note. Step one, identify, check whether the differential equation given to you is linear or nonlinear. If it is nonlinear, before you could take the Laplace transform, linearize it. Then the next step is to take Laplace transform. Take the Laplace transform. Step one. I know there's a hidden step here where you have to linearize, but at least I've been able to explain that to you. That's step one. Step two, what you have to do is you need to express or manipulate the expression that you obtain after taking the Laplace transform in this form, ys equals to qs over p of s. So write the Laplace domain expression as a ratio of two polynomials. You write it, and step three now, you need to factorize the denominator. Factorize the denominator of the characteristic equation. Factorize PS. And then when you factorize, within this step, you need to perform the partial fraction expansion. These are the steps involved in the inverse of Laplace transforms. Step three. And then step four, you take the inverse Laplace transform. Once you do that, you're going to obtain the solution in the T domain. So these are the 4 steps. Please note that step 3 can easily be bypassed. Easily. The reason is that if this expression, if step 2 yields expressions or functions that can be found as an entry in the condensed tables of Laplace transforms, you can just go check if whatever that you obtain here as an entry in the condensed tables of Laplace transform, you can inverse Laplace directly, skipping step 3. So step 3 has been designed to rearrange the functions so that they find entries in the tables of Laplace transforms. So step 3, it's not always a must. You can bypass it if needs be. All right. So this is very important to note. So now we're going to talk about some forcing functions, right? It's part of the dynamic behavior of a chemical process. Okay, there's a hand that has been raised. Yes, go ahead, go ahead. So your phone is Galaxy S8. I don't know what's your name. Please, you're welcome to speak up.
I wanted to ask about what we were doing earlier. So,
oh, yes.
Yes. I wanted to ask, what do we do when we have, let's say, S squared at the bottom? So we have to turn that S into a 0. We have to plug as a -1, let's say. Maybe we have at the bottom S squared plus
Are you
1.
referring to a particular example, or you've got your own example in your mind?
No, I can refer to an example. This way
is it the example that we've just done, or another example?
Okay, it's an example. It starts. Let me check. I think it starts 3.
See, we're not doing that questions now. We're not doing that questions now, because otherwise I won't be able to finish. You see, that's why we have tutorial sessions for you guys to ask all the questions. So what I can do is, but just pose your question first, and then I'll see.
Okay. Okay. Can I continue?
Yes.
Asking.
Yes.
Okay. So what if at the bottom we have S squared plus 4, and then we have to turn the S into a -4 in order to get C1, let's say, for an example.
No,
so
when you have S squared, you say you have S squared plus 4 in the denominator.
Yes, and at the top maybe we have C1.
C1,
for an example.
Yes.
So we have to turn this S squared into a -4, right?
All right, and then?
But if we turn this into a -4, it will be a +4. So it won't be a 0 because we are looking for 0.
If we set S squared plus 4 to 0, is this what you mean?
Yeah, yes.
And then we're going to have S squared equals to -4. Am I following you correctly?
Oh, okay. No, it's fine. I was doing it wrong. It's fine. No, I get it.
Okay.
Thank you.
Okay, you're welcome. So we're going to have, you see, what we're going to do is I'll give you that questions in advance, and then we're going to have a tutorial session. So if you happen to still fall behind in terms of that questions, you're welcome to go to speak to me via the class rep about organizing another tutorial session. We're doing it online, and I'm busy doing something else. I'm done with lectures at UKZ, and we can always schedule a that session where we could go through other questions. All right, so just speak with the class rep, and then he can contact me, and then we can schedule another third session if needs be. So we're going to, okay, there we go. I was talking about dynamic behavior of chemical processes. All right, so let's consider a chemical process shown here like this. So we've got an input. So this is our chemical process, right? Let me just call chemical process. So by the way, our lecture won't be interrupted. I just decided to upgrade my Zoom. So we're just gonna go for 1.5 hours because Teams was also giving me a problem. Just decided to upgrade my Zoom. So we have outputs. All right. So if a change is induced or introduced in the input variable, all right, then a change in the output is likely to be observed. So this explains the dynamic behavior of a process. So if you've got your inputs, chemical process and outputs, if you introduce or induce a change in the input variable, there's a high likelihood that there will be a change in the output. So there exists many ways of inducing changes in input variables, and these ways are referred to as forcing functions. All right, I'm going to repeat myself again. We have this process. So if you introduce a change in the input variables, there's a high likelihood that there will be some changes in the output variables. And there exists a number of ways to induce or introduce changes in input variables. And these ways are referred to as forcing functions. We're going to talk about forcing functions. So the first one, there exist many, but in this module, we're just going to stick to two that we're going to use most often. We're going to look at the step function and two, the ramp function. Let's focus on the step function first. An example of a step function is, let's consider you've got a steam valve. You've got a steam valve and you are tasked to open the steam valve at time t equals 0 so that the heat changes by m units. For example, so you've got a steam valve that you need to open at time t0 until the heat, increases by m unit, for example. So this is what we call a step change. We go from some value to another suddenly. So step functions are referred to the sudden change in the input variable. Hence, we say, for example, one of the characteristics in industrial process is that there can be changes. Changes can be subject, so the input variables can be subjected to sudden and sustained input changes. So when you have, another example is when you have a reactor feedstock that could be changed quickly from one supply to another. And this is likely to cause a change in important variables such as feed concentration and feed temperature. So such changes, or I would say such sudden changes, can be approximated in maths by what we call step functions, or we can call it a step change. And mathematically, this can be written as us of t. So this is a step function where time is the variable, is equal to 0 when t is less than 0, or m when t is greater than or equal to 0. What does this mean? This firstly is what we call a piecewise function in mathematics. It is a piecewise function, and its graphical representation is as follows. So you've got your step function, and this is your time t. So at time t0, all right, we assume that before 0, which is a steady condition here at 0. So at time t0, you open the valve so that m units is released. And then there'll be a steady state condition. This is a step function, which corresponds to the mathematical expression when t is less than 0, our function is 0. T less than 0, because this is your t, your axis, t-axis. This part here is t greater than 0, and this part is t less than 0. So when t is less than 0, the step function is 0. However, when t is greater than or equal to 0, which starts from here because greater than or equal 0 is included in our interval, when t is equal to 0, the function is m. T greater than or equal to 0, our function has. So this means that there has been a sudden change of which the magnitude is m. So you open your steam valve, all right? So the change from the initial value to the other value, we say that there's a change of magnitude m. This is an explanation of this graph or this function. And this is quite common in industry, where you induce a step change in the input variables and then observe what will be the output variables. So instead of just changing maybe periodically or gradually, you could also induce a change in the input variables by a step. You go from 0 to 10, for example, a sudden change from one value to the other. We also have other changes where the change occurs gradually, like there's a slope. And a typical example is when you have a steam valve that you open gradually until a desired value has been reached. You do not open it suddenly, but you open it gradually until a certain value has been reached. And that function is what we call the ramp function, and it's what we're going to look at next. But what is the Laplace transform of a step function? The Laplace transform of the step function is m over s, where m represents the magnitudes of the sudden change, right? So if the magnitude is 3, then you're going to have 3 over s. But in this case, the magnitude is m. And it is important to note that us, which is a step function, is defined as a deviation variable That is the change from the current steady state. Everything else will be much clearer as we progress with examples. So let's look at the other function, forcing function. So the ramp function. As I mentioned earlier, industrial processes often are subjected to inputs that drift. That means they gradually change upwards or downwards for some period of time with roughly a constant slope. An example is when you have a steam valve that you open gradually. And sometimes when you open, as we said, so the changes, occur with a constant slope, all right? So sometimes the ends of the slope signifies that if you opening a valve, that means that you've reached the ends of, so the valve is fully opened. That means that's the end, or the end of the slope could also mean that you've reached the desired value. All right, but when you open, it could also mean that you've fully opened the valve. And also, in some instances, set points are sometimes ramped from one value to another, then instead of making a sudden change. And mathematically speaking, this function is referred to as UR of t ramp function, and it is also a piecewise function where it is equal to 0 when t is less than 0 and equals to at when t is greater than or equal to 0. So the graphical representation of this piecewise function is as follows. So you've got your, the y, this is now moving, all right. Let's go back. So the graphical representation of this function URT in terms of t. So here, when t is equal to 0, when t is less than 0, our function is 0. So in this region, t less than 0, URT is equal to 0. However, at time t equal to 0, there is a change which happens gradually because this is a linear function of which the slope is a. So we say that when t is greater than or equal to 0, URT is equal to AT. This is a linear function. And the slope is equal to A. In some instances, the end of the slope could mean the valve is fully open or we've reached the desired value. So this is the graphical representation of this function. Again, the function URT is a deviation variable. Guys, if you joined us, please mute yourself. We can hear some noise in the background. Is a deviation variable. Right, and the Laplace transform of the ramp function is equal to a over s squared, where a is the slope. Be careful. So if the slope is 10, then that's going to be 10. We also have other functions. For example, rectangular pulse function. We're not going to look at it, but it looks like this. So rectangular pulse function. So the graph representation of this function looks like this. We could assume that this is a time t0. So initially, the process is at steady state. If we call this time 0, at time t0, a sudden change, there's a change. It goes up, change of magnitude m, for example. So once we at m, example, a typical example is when you have a steam valve, you open it until a certain value has been, a desired value has been reached. You leave it open for a duration of time, let's say b, until b time, then you close so that the system goes back to the initial steady state. So this function is referred to as rectangular pulse function, but we're not gonna do much about it, but just for your information, you know what's the other forcing function. So the forcing functions will come in handy as we get into transfer functions, all right? So everything that we've covered leads to the transfer function, because that's why I told you it's very important that we have a session on linearization. If you still have issues with linearization, you're likely to struggle everywhere else, because we won't give you linear differential equations. We will give you non-linear differential equations so that you have to linearize them using the Taylor series expansion. So it's very important that we have the catch-up session on linearization, just so that some student can be on par with us. So next step is transfer functions. Or transfer function. Definition. A transfer function is an algebraic expression for the dynamic relation between a selected inputs and outputs of a process model. I'll write it down. So I'll refer to it as TF. Is an algebraic expression for the dynamic relation between a selected inputs and outputs of a process model. One of the definitions. There are many. But it's also important to note that a transfer function can be derived only for a linear differential equation, because Laplace transform can only be applied to linear equations. And again, if the model is non-linear, then it must be linearized first. I'm repeating myself more often on this because I know that students end up forgetting the linearization part. Once you forget it, the rest becomes zero. I won't even look at it. So it's very important that you remember to linearize when needs be or if needs be. So if we consider a single processing unit, a CISO, with a single input and single output. So let's consider a single processing unit. With single inputs and single outputs. And we refer to this as CISO, system. All right, so this is represented as follows. F of t, you have your inputs, you have your chemical process, now you have your outputs. Single input, single output. Remember that a process model is represented in the T domain. A process model is represented in the T domain, whereas a transfer function is generally represented in the S domain. So then the transfer function of this process will be represented in what we call block diagram. So instead of the process in the middle, we're going to have a transfer function, which is denoted by GS, and the output will be YS, and the input is F of S. So this is presentation of a transfer function, and it is done block diagram. Transfer function in the S domain, process model in the T domain. Please take note. Just an introduction. So let's consider our process. We've got our process, which has an output, YT, and an input, F of t. Let's assume that our process is described by an n-order linear differential equation. So our process is defined by this differential equation. And this is equal to B F of t. So our assumption is that this is a linear differential equation. Anyway, it is a linear differential equation. So if it is a linear differential equation, we can take the Laplace and then find the transfer function of this process. But if the system is initially a steady state, that means SS, we can state that y of 0 is equal to dy over dt at t equals 0 equals to second derivative of y with respect to t at t equals 0 is equal to n minus 1 derivative over dt n minus 1 at t equals 0, that is equal to 0. So if the system is initially at steady state, we can just assume that all these derivatives and y at 0 is equal to 0. If we assume that, then we can take the Laplace of the differential equation. So that means Laplace of a n dn y over dt n plus the Laplace using the properties a n minus 1 d n minus 1 y over dt n minus 1 plus, and we have Laplace a1 dy over dt plus the Laplace of a naught y. This is equal to the Laplace of b times f of t. Assuming the steady state conditions, so this, the Laplace transform of this quantity here is equal to s to the power of n. There's a coefficient an times s to the power of n y s. Please, if you can't see clearly, you're welcome to check the condensed tables of Laplace transform. And this will be equal to a sub n minus 1 Sn minus 1 y s plus a1 s y s plus a naught y s, and this is equal to b times f of s. Taking ys out as a common factor, mean with ys will be equal to, let's just go stepwise, a sub n Sn plus a sub n minus 1 Sn minus 1 plus a1s plus a naught is equal to b times f of s. So y s over f of s is equal to b over an Sn plus a sub n minus 1 Sn minus 1 plus a1 s plus a naught. Note that y s correspond to the outputs and fs correspond to the inputs. So this quantity here is what we call the transfer function, and it is denoted by capital G of s. As we said, the transfer function is an algebraic expression for the dynamic relation between a selected inputs and outputs of a process model. So we can write and say the transfer function of this process is ys over f of s. Remember that transfer function is in the s domain, always. All right. So if, for example, just gonna write g of s is called the transfer function. So if, for example, you have 2 inputs and 1 output, this could also be considered as multiple inputs and a single output system, and we call it MISO. That means more than 1 input. So if the process has two inputs, that means f1 of t and f2 t, then the output is equal to G1 S times F1 S plus G2 S times F2 S. So when you have two input variables and a single output variable, I'll try to do it. So this is the description of the model, process model. We've got two inputs, F1 of t and F2 of t into the process. And you've got a single output, y of t. So we want to find the transfer function of this process. Again, there's a question. Okay, I'll go slow. So I'm gonna go back a little bit. Maybe some student got lost. I'll go back to the transfer function. It's very important that everybody understands. I started by defining a transfer function. I told you it's an algebraic expression for the dynamic relation between a selected inputs and outputs of a process model. All right, and I said a process model is represented in the T domain, whereas the transfer function of a process is represented in the S domain, hence the difference between these two. And this representation is referred to as block diagram. So if I ask you to sketch or to give me a block diagram of a process, that means I want you to do it in the S domain, not in the T domain. All right, and then we considered a SISO, which is a single inputs and single outputs system. All right, we've got a single input f of t and single outputs y of t. And if our process is described by a differential equation, which is linear, by the way, then we can take the Laplace, because what we want is the transfer function of this process. So it's important that we take the Laplace so we can be in the S domain. So because this differential equation is linear, we can take the Laplace transform. And if the system is initially at steady state, we can assume that these differentiations are equal to 0. And considering this assumption, we can take the Laplace of the ordinary differential equation. Considering the condensed tables of Laplace transforms, we obtain each term of the new expression, where ys is it's common to all the terms on the left-hand side, so we can take it out and then express the whole expression in terms of ys. So ys over f of s gives us b over this equation. And b over the whole quantity here is what we call the transfer function. Again, it relates, selected inputs and outputs of a process model. Remember, ys represents the output variable in the S domain, and f of s represents the input variable in the S domain. So now if the process does not have a single input, but two input variables, f1 of t and f2 of t, then this is how the output is represented. So I'm going to show you how we got to this expression. This is the diagram of our process model. So we assume again that this process is described by a linear differential equation such that an dny over dt n plus an minus 1 dn minus 1 over dt n minus 1 y plus a1 dy over dt plus a naught y, which is equal to b f of t. But in this case, we do not have a single input, but two input variables. So we're going to have b1 times f1 of t plus b2 times f2 of t. If we consider the same assumptions as previously, so all the first and second derivatives at 0 will be equal to 0, and take the Laplace transform, and rearrange, you're going to end up with, you take ys as a common factor, going to remain with an Sn plus an minus 1 Sn minus 1 plus a1 s plus a naught, and this will be equal to b1 f1s plus b2 f2s. All right, and then y of s will be equal to b1 over an sn plus an minus 1 sn minus 1 plus a1 s plus a naught times f1 f of s plus b2 over an sn plus an minus 1 sn minus 1 plus a1s plus a naught times f2s. Remember that this corresponds to transfer function. So now we have y of s that is equal to g1 s times f1 s plus g2 s f2 of s. All right, just simple manipulation. So now, what is the block diagram of this model, of this process? Remember that we've got two input variables. We've got f1 s F to S. Each input goes into a transfer function. And then these two, they get added to give us the outputs variable. So this is the block diagram of the process that has two input variables and a single output variable. So let's say you have multiple input variables and we ask you, no, multiple input variables, yes. We go from F1 to Fn, for example, and we ask you to provide the block diagram. Multiple input variables and a single output variable. So we have multiple inputs variables, or just multiple inputs and single outputs. So the block diagram of such a process will be, so we're going to have, for each input, you're going to have a transfer function. So if the first input is f of 1s, f of 2s, fns, g1s, g2s, gns. So all these give us outputs that are going to be added to give us the outputs. How you represent a block diagram of, this could also be called a MISO. You have multiple input variables and a single output variable. All right, so something also worth noting is the steps necessary in finding the transfer function of a nonlinear process. Again, if the process model is nonlinear, linearize the model. And step 2, represent the linearized equation or the linear equation in terms of deviation variables. That's very important. But one question though, what is the use of transfer function? I'm sure you're wondering, what is the use of transfer function? It's always important to know, why are we doing something? What is the use of transfer function? Again, I'll just abbreviate it as TF. All right, I don't want to answer this question, but I want to explain, and then we're going to answer this question, and then we're going to end there. All right, let's consider a seesaw. A seesaw system. So this is representation of the process. We've got inputs in the T domain and outputs, YT. In the S domain, this is f of s into a transfer function, not the difference, y of s. In the S domain, we've got a transfer function, not the process. Be careful. All right, S domain, and T domain. All right, so here, if one knows the process model, that means they can derive the transfer function. Remember how we obtained the transfer function of the previous seesaw system? Everything went from the process model, which was the differential equation. We took the Laplace transform, and now we're able to write the expression in the Laplace domain. So if one knows the process model, they can derive its transfer function. So if one knows the process model, they can derive its transfer function. Easily. So we're going to assume that the process model will be given to us. In other words, GS is given. So if the process model is given, that means GS is also given because it can be obtained easily. So let's look. You've got the transfer function. How is it useful? It is useful in a way that you can easily observe the dynamic behavior of a process if you know the transfer function. I'll give you an example. Let's consider a process. That is initially at steady state. It is initially at steady state, and you introduce a step change in the input variable. All right. First step, let's consider a process that is initially at steady state. Second step, induce a change in the input variable. So for example, a step change. All right, a step change of magnitude A, for example. You can take the Laplace transform, very easy. And it will be 1 over S. So you've got a process that is initially a steady state, and then you induce a change, and that change is assumed to be a step change of which the magnitude is A. And we know that the Laplace transform of a step change of magnitude A is A over S. That's okay. And something else that we know is that the transfer function, which is known from the process model, is defined by y of s over f of s, where this is the output variable and this is the input variable in the S domain. So we can rewrite this and say ys is equal to g of s times f of s. I hope I haven't lost anybody else. So we've got this. We know the transfer function. we induce a change in the input variable. Because we know the transfer function and we know the change that we introduce in the input variable, we can determine the output result. I'm going to repeat again. You'll be given the process model. Once you have the process model, you can derive the transfer function, which is g of s, so given to us. If you want to know the dynamic behavior of the process, try to induce a change in the input variable and then observe the output. So if you induce a step change of magnitude a, because we in the S domain, we need to take the Laplace and have it as a over s. So if we induce a step change in the input variable, knowing the transfer function of our process, we can be able to see what the output variable will be. Hence, we say the use of a transfer function is to observe the dynamic behavior of a process. The use of a transfer function is to observe the dynamic behavior of a process. Because once you induce a change in the input variable, you're going to observe, going to get the output in the S domain, but to get the output in the T domain, you need to inverse Laplace y of s. Inverse Laplace transform of ys to obtain yt. It's very important to note. And something that's also worth noting is when you are given a transfer function, we know it is y of s over f of s because it relates selected input and selected output of a process model. This is a ratio of two polynomials. We can also say the transfer function is q of s over p of s, just a ratio of two polynomials. So the roots of q of s are called the zeros of the transfer function or the zeros of the system. Of the transfer function or the zeros of the system. And the roots of P of S, our characteristic equation, are called the poles of the transfer function. So, in summary, once you have a process model, you can determine the behavior of a process easily, and I've shown you how to do that. You can just induce a change and be able to see the results, the output variables. All right, so once you do that, you can just induce different changes. We've covered step change and ramp change. So far, I've just briefly introduced you to the step change, but we'll do more examples because with transfer functions, we'll do plenty of examples. So we're not gonna meet on Wednesday, it's public holiday unless you want to. So otherwise, we're going to meet again on Friday, where we'll do plenty of examples under transfer functions. So it could take us 2 double periods to do the examples and then move to the first order system. Right, so there was a suggestion that we meet tomorrow for the catch up on linearization. Yeah, tomorrow is fine, but let it be in the morning. Let's say 9 o'clock. So I'll send an invitation to everybody if you're okay with 9 o'clock, or else I can avail myself from 8 to 11. All right, so between 8 and 11, pick a date, pick a time and the duration so that we could cover that and then get it out of the way. So that's it for today, unless there's no question in the chat, no hands up. So that's it. I will, this has been, it's being recorded. So